Bismillahirrahmanirrahim. This is another video with magnetic circuit with air gap, and this is problem number 1.9 of the second textbook. So let's see, the magnetic circuit in figure 1.6 consists of rings of magnetic materials in a stack of height h. So this is the circuit dimensions or the core dimensions, and when say stack of height h, that means it is stacked like this. So one ring over the other ring plate and the third ring plate. So this is how this core is made. Now let's see what are the dimensions. It has 65 turns and the outer radius is 4 centimeter and the inner radius is 3.4 centimeter. The magnetic material has infinite permeability and the core gap is 0.2 centimeter and the height of the stack is 2 centimeter. What we have to find is, we have to find the mean core length. So the length of this core, mean core length, that means we have to take the average of the outer and inner and then find the perimeter. Then the cross-sectional area from here, and then we have to find the reluctance of core and that of the gap, inductance L, current I required to operate at an air gap flux density of Bg is equal to 1.35, and the corresponding flux linkages lambda of the coil. So first let's find out the mean radius. So we add the 2 and divide it by 2, so we'll get a radius which is somewhere here in the middle of the 2. So we'll use that radius, which is 3.7 centimeter, to calculate the core length. So core length is 2 pi into r, the total core length, but from there we have to subtract this 0.2, that is length of the air gap. And so putting the values, 2 pi, r is 3.7 and minus 0.2, so we get an answer of 23.05 centimeter. This is the mean core length. Now we have to find the area of cross section. So this is the area of cross section, that means the height multiplied by the width. So the cross-sectional area AC is R outer minus R inner. So this will give you this length and multiply by height. So 4 minus 3.4 and multiply by height 2 centimeters. So we get 1.2 centimeters square as the cross-sectional area, and which can be converted into meters, which we'll be using subsequently. It will become 1.2 into 10 raised to the power minus 4 meters square. Now part 2, reluctance of the core Rc and that of the gap Rg. Now if you remember, this permeability is infinity. That means there is no resistance or reluctance offered by the core, and therefore we can straight away write that Rc is equal to 0. Now for Rg we'll use the formula that we know. It is the gap dimension divided by the permeability of air, 4 pi 10 raised to the power minus 7, and the cross-sectional area. So the cross-sectional area of the core and the air gap, they remain same, we are assuming. So G was 0.2 centimeter. This we convert into meter, so it will become 0.02 meters. 4 pi 10 raised to the power 7, and area of cross-section we had found in meter 1.2, 10 raised to the power minus 4. And so solving, Rg is 1.327 into 10 raised to the power 7 ampere per Weber. The third point was to find inductance L. We know this formula, N square over R total is the inductance. So N square and R total is Rc plus Rg. In our case, Rc is 0 and Rg we found out from here. So by calculating, the inductance comes to be 0.318 millihenry. Now the fourth part, we have to find the current required to operate at an air gap flux density of 1.35 Tesla. Okay, the flux density is given by the flux divided by area, and flux we could find from this Ni over R, and putting the value of R, and this will come to be like this here. So from here, B is flux divided by A, area, and if you put in the value of area here, then this putting the value of flux divided by area, so we'll get this term. Mu 0 area will get cancelled, Ni and G. So this is the final value. Now from here we can calculate I. So we keep I on one side, move this G multiplied by B and divided by this term mu naught N. So we'll use this formula to calculate the value of I. So plugging in the value, B was 1.35, G gap is 0.002, mu naught 4 pi 10 raised to the power minus 7, and number of turns 65. So we get the current to be 33.05 ampere. And lastly, we have to find the corresponding flux linkage lambda of the coil. Now flux linkage is actually total flux. So we multiply the flux with the number of turns to get flux linkages. Now we know the number of turns 65, and we can calculate the flux by this formula, but there is an easy way. We can use this definition. Since we have the flux density given, we also know the area, so we can replace flux by P into A. So here we are replacing flux by B into A, so it will NBA, and now we have all the values. So N is 65, B is 1.35 Tesla, and the area of cross section 1.2 10 raised to the power minus 4. So the answer is 10.53 milliweber. So this is how we solve this type of problem. Here is a question that you should try. Again, just based on the previous one, and I hope this answer is correct, so try to find it out. Thank you very much.